Good morning, students. So we are going to start today the new unit in quantum mechanics 2, which is on perturbation theory. So this is about time dependent perturbation theory. So far we have dealt the Hamiltonians which do not depend on time so far, and of course in the quantum mechanics 1 we dealt so many models like quantum well problem, barrier problem, infinite quantum well, finite quantum well, then hydrogen atom, harmonic oscillator. In all the models, we calculated the wave function and energy levels, which are stationary states, and discrete energy levels, which are time independent Hamiltonian. And we were able to get all the solutions. And these solutions are exact solutions. We solved Schrödinger equation, time independent Schrödinger equation, second order differential equation, and we could be able to get some solutions. They are all exact solutions. And few models, they are all simple systems. But actually speaking, the models which we are going to deal are complicated systems. They are all complex systems. In nature, lot of systems are complicated and the complex systems exist, for which we can't solve the exact solution. So we'll have to go only with the approximation methods. So we will get only approximate solutions, no other way. So these are all time dependent one. So total Hamiltonian will be your unperturbed Hamiltonian plus time dependent Hamiltonian, and together we call this as total Hamiltonian, which depends on time. So for unperturbed Hamiltonian, we will use only the exact solution. For perturbed Hamiltonian, perturbation means disturbance, small disturbance. For example, we are going to apply magnetic field. The disturbance will be there, especially on the spectral lines. Suppose if we have a line, spectral line, only single line, we are going to apply magnetic field. So there will be 3 or 4 or 5 lines will be there. So 3 lines, what we call this as a Zeeman effect. More than 3 lines, what we call this as anomalous Zeeman effect. So there are something like that. For example, we take the applications of the electric field. The spectral lines will split. So those splitting of spectral lines in the electric field or magnetic field are called nothing but perturbations, disturbance. Even raising the temperature, phonon effect. So all those things, even the radiation which are coming out from the universe, that will disturb the system. So they are called perturbation. So small disturbance. And these perturbations should be very, very small. So in all the cases, we are able to solve only with the power series method. We are going to expand. We are going to have a corrections to the energy levels. Unperturbed system, we will have exact solution. We will have particular energy level. Okay, now we are going to add some perturbation. When you are going to add the perturbation, the energy levels will be shifted. So we will have to add the Hamiltonian, we will have to get the solution, these approximate solutions, we are going to add the exact solution. When you are going to add the exact solution, we are going to have the corrections to the exact energy levels. So the energy levels will be shifted. Okay, and we are not going to solve any Schrödinger equation for the perturbed system. We are not going to solve. Either we are going to use some matrix method, which you are going to see now, or otherwise we are going to solve through power series method, expansion method. So this is the idea. But as I said, in nature, almost in all complicated systems, complex systems, we need to have only Hamiltonian which explicitly depends on time. For example, when radiation falls on the matter, so when matter is interacted with the radiation, and the atomic levels, they will go from one level to another level. So what we call this is excitation, out of which we can get the structure of the atom or structure of the molecules. So whenever there is a structure of the atom or molecules we want to know, then surely we will have to go only with a Hamiltonian which explicitly depends on time. So we will have to use only time dependent perturbation theory. So in this unit, we are going to discuss all the topics, the time dependent perturbation theory, constant harmonic perturbation. So there are 2 types, constant harmonic perturbation. Of course, very important one is Fermi's golden rule. So this is very, very important one, and it is given as Fermi's golden rule. Golden rule. So golden means, so you have to give much more important. This a rule which connects the experimental and theoretical part. So that's why it's given as golden rule. So transition probability, Einstein's A and B coefficients. Then we'll have to go with two approximations, adiabatic and sudden approximation. Then we will be dealing with the semi-classical treatment of an atom with electromagnetic radiation. Just now I said it's a very important one. And the selection rules for the dipole transition. And as I said, the time independent and time dependent Hamiltonian, they come under approximation methods. So we are not going to have any Schrodinger wave equation. Okay, we are not going to have any exact solution. So they are all approximate methods, like using power series or otherwise we will be using matrix method. Okay, so in time independent Hamiltonian, which we discussed already in quantum mechanics 1, and Zeeman effect, Stark effect, ground state of helium atom, WKB method, variation method, they come under time independent perturbation theory. And time dependent perturbation, as I said just now, when light interacts with the matter. So whenever you want to find out the structure of the atom or molecules, so surely we need to go only with the time dependent perturbation. So there will be an excitation will take place. Like for example, it absorbs and emits. It absorbs the radiation from outside, it goes from one level to another level, so transition level will take place, and absorption and emission almost in all the samples which we do in the lab, so that will be subjected to the electromagnetic radiations. Only then we can get the structure of the atom, spectral lines. So atomic physics, especially in spectral lines, it is used. So absorption spectra, emission spectra, scattering experiments, and also nuclear particle reactions, especially nuclear disintegration, half-life period, nuclear reactions. So in almost in all the areas, this time-dependent Hamiltonian, time-dependent perturbation is used. Okay. So time-dependent perturbation theory, we are going to discuss in detail. We have already studied many of the systems, simple systems, what we call the simple systems, that can be solved exactly. Okay, we use Schrodinger equation and get the solution. So we will have only stationary solution for any discrete energy levels. For example, hydrogen atom, quantum well problems, harmonic oscillator, and so on. Furthermore, many of these systems are only approximations to real systems. We will need approximation methods to study the wider range of complicated and complex systems. So complicated and complex system only exists, okay, 90%, more than 90%, when light interacts with the matter. Almost we can have lot of experience when light interacts with the matter. Most interesting systems involve transition in energy as a function of time. Okay, emission and absorption. So they all depend on time. The simplest model of this kind is two-level system. So as I said just now, when light interacts with the matter, so we have the transition will take place from ground state to excited state. So ground state to excited, because it absorbs the energy, it goes to the excited state. And after some time, from excited state to it comes to the ground state by emitting the lines. So absorption and emission both will depend on time. So here a perturbation theory is applied with when the Hamiltonian depends explicitly on time. So h of t. But however, this h of t is very, very small. It should be small. So perturbation should be very, very small. That's why the strength of the perturbation, which we have already denoted in quantum mechanics 1 as lambda, that should be very, very small. So very important one more question, as I said earlier, lambda, the value of lambda lies between 0 and 1. So this value will be always less than 1. So this must be very, very small. So this factor should be very, very small. And total Hamiltonian, h equals h naught plus lambda h prime of h1 or h prime of t. So this depends on time. This does not depend on time, for which we have already solved Schrodinger equation, and we will have exact solution. Okay, so this is unperturbed Hamiltonian, this is perturbed Hamiltonian, put together is a total perturbed Hamiltonian. Okay, is it clear? So we are going to add some corrections. The corrections can be either 0th order, first order, second order, depending on the values of your lambda. Okay, so one can evaluate the probability of finding the system in any particular state at any later time, and the Hamiltonian is added by time dependent perturbation. It gives us a discussion for the probability of transition of the system from one unperturbed transition state to another perturbed state. So earlier, when light interacts with the matter, before that, so we will have only unperturbed system. The moment when light interacts with the matter, this will go into perturbed system. So that's why unperturbed state to perturbed states. Hence the wave function will have perturbation. Induced time depends. So total Hamiltonian, which depends on time, is unperturbed plus perturbed Hamiltonian. Your lambda is the strength of perturbation, and lambda should be very, very small. So these factors should be very, very small, less than 1. Okay, this is mainly used in, as I said, in atomic physics, particularly in spectral analysis. Okay, in which we have emission and absorption. In addition, the quantization of energy and time-dependent perturbation are applied in many applications. It is also used in nuclear physics, as I said, particularly in nuclear reactions, disintegration, half-life period. The theory of time-dependent perturbation developed by Paul Dirac. Okay, it's often called as theory of variation of constant. So now main theory starts, and we are going to have these first slide and second slide. We are going to deal only with the unperturbed Hamiltonian. So wherever you find 0 or not, you just think it of about only unperturbed Hamiltonian. So let us consider the unperturbed Hamiltonian with the wave equation depending on time. So you have h naught psi naught equals, of course, h naught psi naught equals E psi naught. We know already. So eigenvalue equation for any unperturbed Hamiltonian. E is an operator which can be replaced by IH cross d by dt. Okay, so E psi equal IH cross d psi by dt. Psi is missing, so d psi by dt. So I just multiply and divide by I. So that will give me minus h by h cross by I d psi by dt. So I can replace this by this. So h naught psi naught, which is equal to, instead of E, substitute this. So that will give you equation 7.1. Okay, any doubt? So now I bring d psi naught here, and I bring the psi naught to this side. So d psi naught divided by psi naught, which is equal to other constants, minus, you have I is here, so I h naught divided by your h bar partial dt. Any doubt? So I have separated psi naught and I have separated constant and dt that side. I am going to integrate on both sides. So I am going to integrate on both sides. Integrating, that will give you answer as log psi naught. So log base E psi naught, which is equal to, integrating will give you t. So minus I h naught t divided by h bar. Raising this equation by exponential. So that will give me e to the power log base E psi naught. And that will be cancelled. You have psi naught, which is equal to e to the power minus I h naught t divided by h bar. Okay, equation 7.4. Any doubt? Okay, so now we know that h naught psi naught equal to en naught psi naught. We know already this. So eigenvalue equation for any unperturbed Hamiltonian is given by this. Okay, so now just using this equation, psi naught equal to e power I h naught t by h bar is the earlier equation. You substitute h naught psi naught here. So that will give me e power minus I en naught t divided by h bar psi n0, equation 7.5. Okay, so in earlier equation we have h naught. Okay, just substitute h naught psi n0 equal to en0 psi n0 here. That's all, you will get this equation. So this is the expansion wave function. So we can expand all the wave functions, like for example c1 psi 1 plus c2 psi 2 plus c3 psi 3, which is equal to, we can write this as sigma cn psi n. So instead of cn we can write an psi naught. So we can, this is expanding wave function. So when you are going to have all the wave functions, they form a complete and orthonormal set. Okay, all the wave functions are orthogonal to each other. So whenever you find ground state, the wave function will be normal wave function. The moment when light interacts with the matter, it goes to the excited state. All the excited states will be perpendicular to the ground state wave function. They will be always orthogonal. So this is nature. I repeat, the wave function for all the ground state will be normal. The wave function for all the excited state will be always orthogonal to ground state wave function. Is it okay? So that's why, as I said, this will be a complete one. Also this orthonormal set. So that the total wave function can be expressed as a linear combination, C1 psi 1 plus C2 psi 3 linear combination. So using expansion theorem, the total system psi naught can be expanded using this equation 7.6. Okay, now psi naught is given as equation 7.5. So just a substitute for psi naught will give you this equation 7.7. Is it okay? Instead of psi naught, you substitute this expression. You will have the total psi naught can be written as exactly equation 7.7. So here an is nothing but expansion coefficient. Okay, expansion coefficient, which is nothing but a constant. And psi n 0, the wave function psi n 0 are eigenfunctions of time independent. So because we are talking about only unperturbed Hamiltonian, so that's why it is time independent Schrodinger equation. Okay, so these two slides they discuss only about the eigenvalue problem for the time independent equations. It's unperturbed Hamiltonian. So now we are going to have the time dependent one. So time dependent is introduced in the second term, time dependent Hamiltonian. So as I said, total Hamiltonian equals unperturbed Hamiltonian plus time dependent Hamiltonian. So it's given. So H0 is unperturbed Hamiltonian and H1 is the perturbed Hamiltonian, which depends on time, and of course lambda, the strength of the perturbation factor, and lambda should be very, very small. Okay, so now this is H1 is a slowly varying function of time, hence the perturbed equation is given by this equation, because we know that H psi equal to E psi, so this operator can be replaced with this one, so this can be written as like this. So instead of H psi, you just substitute H0 plus lambda H1 psi, which is equal to your E psi. I repeat, H psi equal to E psi, E is replaced with this operator, okay, and your H is replaced with H0 plus lambda H1. Is it okay? Equation 7.9. H psi equal to E psi, that's all. H is given as this expression and E is written as exactly like this. So minus H bar by I partial d by dt. And expansion theorem, your psi of t equals a n of t. This time the expansion coefficient explicitly depends on time. See, look at here, does not depend on time, it depends on time. Okay, it depends on time, and wave function also depends on time. You substitute here. So we have H0 plus lambda H1. Instead of psi, you substitute this expression equals minus H bar by I d by dt. Instead of psi, you substitute this expression. Is it okay? Equation 7.11. Very simple. So left hand side let it be like this. Right hand side is you are going to differentiate. Okay, but both the factors depend on time. Your expansion coefficient and wave function both depend on time. We will have to differentiate. So keeping this as constant, we will have to differentiate this. Keeping this as constant, we will have to differentiate and add. Okay, so in the next step, we are going to differentiate. So we have differentiated. Keeping this as constant, we have differentiated. Keeping this as constant, we have differentiated this. So only there are two factors only. We have two factors. One is expansion coefficient, another one is wave function, which depends on time. So we have differentiated. Now we know that already H0 psi naught equal to E psi naught. So minus H bar I d psi naught by dt. You substitute here. We will get this first term. So a n of t. So this becomes minus H bar by I d psi n 0 by dt. The second term let it be like this. This term also let it be. This term also let it be. And first term and last term. So they are cancelled. They will get cancelled. First term, look at the first term and last term. They will get cancelled. The remaining term will be your second term, the first term on the right hand side. So I have written exactly like this. So equation 7.14. Is it okay? Any doubt? Now multiply this equation by psi m0. Okay, the complex conjugate of psi m0. Okay, psi m0, and we are going to integrate over the space. So we are going to multiply this equation by psi m0 and we are going to integrate over the space. So you will get the equation 7.15. You just multiply. So psi m0 is actually already there. So this becomes dAn by dt. So this psi m0 star psi n d tau. Okay, we are going to integrate on both sides with respect to space d tau. Any doubt?